Hello everyone. In this video, we will be discussing about module 4 in non-traditional machining process. So this module 4 basically consists of two major non-traditional machining process. First one is electrical discharge machining, or else in short form we can call it as EDM machining process, and second part is plasma arc machining. So these two topics will be discussing, and both the machining process will come under thermal energy source. So they are using the heat energy as the source for removal the excess material. So what is electrical discharge machining? So electrical discharge machining, sometimes it is referred to as spark machining process. The reason why it is called as a spark among all the non-traditional machining process available, this particular machining process, we are calling it as a spark. The reason is here the source which will come out from the we can call it as a tool holder or whatever the thing in the form of spark. So and with the help of that spark, and the spark usually will be having the temperature of around 3000 degrees Celsius or 4000 degrees Celsius based on like the electricity amount or high voltage we are providing. The spark will be released, and that spark will be allowed to hit over the surface of the workpiece where we are expecting for the metal removal process. And since the spark plays a major role, it is also called as the spark eroding process, since it is eroding the surface of the workspace and burning. During once the spark has been hit to the surface of the workpiece, it starts vaporizes. The workpiece starts vaporizes, and even it starts melts also based on the temperature what we are supplying. And after the burning, again continuously flushing will be done with the help of a dielectric fluid, and it will be carrying out the excess fluid which was molten, and it is also called as a die sinking or the wire erosion process. So people can call this non-traditional machining process by different names based on the working process and the major components which is present, and the remaining things. And this is a manufacturing process whereby a desired shape is obtained using electrical discharges. So here the electrical discharges in terms of sparks we will be getting, and material is removed from the workpiece by a series of rapidly recurring current discharges between two electrodes separated by a dielectric liquid and subject to an electric voltage. So here again, what matters a lot here is the electrical liquid, dielectric liquid what we are using initially when we are taking it for operation, which is not like a highly sensitive with the current. So once the process has begun, then the dielectric fluid will become like a highly sensitive to the current, and thereby even it provides like a major support in the process. And one of the electrodes here we will be calling this a tool electrode, or generally tool, and sometimes we can call it as an electrode. And other electrode here will be the workpiece electrode, other workpiece. So here what is the main rule for this electrical discharge machining is the tool should be an electrically conductive, and similarly the workpiece also should be electrically conductive. So if you look at the need of this electrical discharge machining process, usually like very difficult to cut materials, examples tungsten carbide, like high hardness alloy steels, like any specific aircraft applications and navy applications. So all those things we can use this electrical discharge machining process. But the important thing is we are limited to use only the metals which are highly electrically conductive. Other elements like composites, like wood, and some other non-metallic elements which is not electrically conductive, such kind of materials we cannot use for the machining by using this electrical discharge process. As the distance between the two electrodes is reduced, the current intensity becomes greater than the strength of the dielectric, at least in some points, causing it to break. Here, the potential difference will be created, and the amount of the potential differences will be created based on the gap what we provide between the tool holder, or else we can call it as a tool electrode, and the workpiece. The recommended range is 0.01 to 0.05. So this is the recommended range, and some places like based on like the potential, like 0.1 to 0.5 mm also is recommended. So moving to the history of this electrical discharge machining process. So this electrical discharge machining process basically allows current to flow between the two electrodes. So here the two electrodes, once again let me confirm, it is the tool is the first electrode, and the workpiece is the second electrode. So the phenomenon is same as the breakdown of a capacitor. As a result, material is removed from both the electrodes. Once the current flow stops, new liquid dielectric is usually conveyed into the electrode zone, enabling the solid particles, we will be calling this a debris, to be carried away. Adding new liquid dielectric in the electrode volume is commonly referred to as flushing. Also, after a current flow, a difference of potential between the two electrodes is restored to what it was before the breakdown, so that a new liquid dielectric breakdown can occur. In 1770, English physicist Joseph Priestley studied the erosive effect of electrical discharges. Furthering Priestley's research, the EDM process was invented by two Russian scientists, Dr. B.R. Lazarenko and Dr. N.I. Lazarenko in 1943. In their efforts to exploit the destructive effects of an electrical discharge, they developed a controlled process for machining of metals. Their initial process used a spark machining process named after the succession of sparks, electrical discharges we call usually, that took place between two electrical conductors immersed in a dielectric fluid. So during their research they got to know that even though like two electrodes, whether it is a negatively charged or positive charged, like in other words we can call it as cathode or anode, but in the presence of dielectric fluid only the spark will be eroded powerfully, and the discharge generator effect used by this machine, known as Lazarenko's circuit, was used for many years in the construction of generators for electrical discharge. New researchers entered the field and contributed many fundamental characteristics of the machining method we know today. In 1952, the manufacturer Charnels created the first machine using the spark machining process and was presented for the first time at the European Machine Tool Exhibition in 1955. In 1969, Agile launched the world's first numerically controlled wire-cut electrical discharge measure. Seibu developed the first CNC wire EDM machine in 1972, and the first system was manufactured in Japan. Recently, the machining speed has gone up by 20 times. This has decreased the machining cost by at least 30% and improved the surface finish by a factor of 1.5. And moving to the general aspects of electrical discharge machining process. Electrical discharge machining process is basically a machining method primarily used for hard metals, are those that would be very difficult to machine with traditional techniques. Just now we discussed, like even have given some examples like tungsten carbide and other carbide alloys. And electrical discharge machining typically works with materials that are electrically conductive, although methods for machining insulating ceramics with EDM have been proposed. EDM can cut intricate contours or cavities in hardened steel without the need for heat treatment to soften and re-harden them. This method can be used with any other metal or metal alloy such as titanium, hornstone, copper, and inconel. You can able to see. So these are some of other like very strong metals which is very difficult to cut in any conventional machining process. So titanium, hornstone, copper, and inconel, like all these metals are like very famous for its hardness and like rare applications. And also applications of this process to shape polycrystalline diamond tools have been reported. And with this, let us wind up this video, and in the coming video we'll just discuss whatever we discussed in the schematic with the schematic point of view. We will discuss even electrical discharge machining, the major components, what kind of dielectric fluids are recommended, and the concentration of the dielectric fluid, and what is the source of power, whether we can use direct current or alternative current, and what is the voltage requirement, whether it is high voltage or low voltage, whatever the atmospheric conditions are like laboratory conditions, whether it can be done, and the gap distance particularly, which plays a vital role. So all those informations we'll be discussing with the help of a like a diagram we will see.